Okay, hey, welcome back everybody. This is our second lecture in Unit 2. And in our last lecture, we talked about atomic structure and subatomic particles. Today we're going to dive more into electrons. And today's topic is going to be valence electrons. So before we start, let's talk about our objectives. So our objectives for today is to identify how many valence electrons are in a given element. So we're able to see an element and say, hey, that element has X amount of valence electrons. We also need to be able to determine how the number of valence electrons affect the properties of an element. So how does 3 valence electrons affect an element opposed to 5, or so on. And finally, we need to be able to predict whether an element is going to gain or lose electrons. So in saying all that, let's dive into what we have today. So what are electrons? Electrons are negatively charged subatomic particles. They are found outside the nucleus, so they are not inside the nucleus. That's only protons and neutrons. And they help determine the overall charge of an atom. Okay, because remember, we cannot change the number of protons. Protons are the identity of the atom. So in order to change the charge of an atom, we must change the number of electrons, or negative charges. Okay, so keep that in mind. Electrons determine how atoms interact with each other. So in other words, I'm saying that electrons are how chemical reactions occur and how atom interaction occurs. Whenever an atom gives up an electron, takes an electron, or shares an electron, that's all going to cause chemical reactions. Notice they're all dealing with electrons, though. We don't take protons, we don't take neutrons. It's all dealing with electrons. Okay, so we have electrons here that we know they're negatively charged. We know they are interacting between elements, like that's what causes the interactions, whether it's giving up electrons, gaining electrons, so on. But we don't know very much about where they're located. Okay, so that's what we're going to be camping out for the next 2 lectures, is how to identify locations of electrons and understanding just about where they're at. Electrons are found in what we call the electron cloud. The electron cloud is basically all the different levels of orbits outside of the nucleus. Okay, you have your central nucleus, and then you have different orbits that come around. So we find all these electrons in different levels or orbitals, and all of them together we call the electron cloud. The outermost level, or the one that is the farthest away from the nucleus, that's going to be called our valence shell, or our valence level. And electrons found on this, those are going to be our valence electrons. These are going to be your most reactive ones. These are going to be the ones that are either given up, taken, or whatever, shared. These are the ones that interact with other elements. So we got our electrons. Electrons are found in different levels, those around the nucleus. Those levels are called orbits. The outermost orbit is called the valence shell, and on that valence shell we have valence electrons. So what are valence electrons? Let's get a little bit more in depth of knowing about our valence orbital and valence electrons. Okay, so as I stated, electrons on the outermost orbital are called valence electrons. So these atoms that are on the outside, farthest away, are your valence electrons. You can think of them like your frontline reactors, or basically the front line within, you want to say an army, whatever. These are the things that are going to cause a reaction. These are the first responders. These are the ones that come out, and they're the first to have anything happen to them. Because they're the first ones that come out and the first ones that react with other elements, they're going to be the factor that determines how reactive an element is in general. So valence electrons, outermost electrons, front line, they're the ones that react with everything. When dealing with valence electrons, we need to know the octet rule. The octet rule is also known as the rule of 8. And basically it states this: for an atom to become stable, they must have an empty, half-filled, or fully filled valence shell. In other words, they need to have 0 valence electrons, 4 valence electrons, or 8 valence electrons. That's where you get 8, octet. Okay, so let's think about this. Atoms in their natural form want to be stable. They want to get to a state in which they can just be who they are, in lack of another better term. These atoms, in order to be stable though, they need to have a fully filled valence shell, a half empty valence shell, or an empty valence shell. Those are the most stable forms of valence shells. So where are we going to go with this? What are we trying to do here? Elements can be categorized on the periodic table by the number of valence electrons they have. This is what produces what we call an oxidation. Okay? We use the periodic table to create oxidation trends and predict how elements interact. So we're going to use our periodic table to say how many valence electrons there are in an element. We assign either a positive or negative oxidation number to a whole vertical column on the periodic table. So if I say column 1, that's going to be hydrogen and everything underneath it in that first vertical column. That's going to have the same oxidation number. So let's go through some trends real quick. One thing I do want to point out is before we start is your transition metals have multiple oxidation states, so they're not going to apply to this trend. We'll later learn how to do oxidation numbers for transition metals. But for the sake of this lecture, let's just get the basic trend down first. So your first vertical column, one dealing with hydrogen, everything in there is going to have a +1 oxidation number. Well, what does that mean? That means they have one valence electron in their valence shell. And it is easier for them to get rid of one negative charge, okay? They get rid of a negative, that's going to leave them positive overall, the atom positively charged overall. So it's easier for them to get rid of one negative charge and be positive overall. So that's where we get the +1 oxidation. So hydrogen, if you get nothing else, just know that hydrogen's column +1. Beryllium, Be, that one's column is +2. Okay, yes, it has 2 valence electrons, and that's 2 away from 0 and 2 away from 4. But it's easier for them to lose electrons at this point than gain them. So they have a +2. Then we go over to boron's column, B. So everything vertically underneath boron, that's going to have a +3 oxidation. That means it has 3 valence electrons, and it's easier for them to lose those 3 valence electrons than it is for them to gain more valence electrons. Carbon, this is your middle point. This is your point in which if you just memorize hydrogen, carbon, and fluorine, then you'll be all good. Okay, so carbon's your middle point. This is going to be your +4. Carbon and anything underneath it has 4 valence electrons. This means they're pretty stable. Does that mean they're unreactive? No, not really, because carbon reacts with a lot of stuff. But it takes more to cause a reaction, and they're going to have stronger bonds because it takes stronger forces to cause a reaction with carbon or anything underneath it. Now we go down to nitrogen. Anything underneath nitrogen. Now we're going to go to a negative number. So there's going to be a -3. So we went from hydrogen +1, beryllium +2, boron +3, carbon +4. Now we're going to nitrogen -3. We're going to go down with negatives now. And so nitrogen has a -3 oxidation state. Anything underneath it, followed underneath it, is going to have that -3 oxidation state. It's more likely to gain 3 electrons and become fully filled than lose electrons at this point. So that means that it has 5 valence electrons. 5 plus the 3 is going to give us our fully filled 8. Then we go to oxygen. Oxygen is a -2 oxidation number. It has 6 total valence electrons. Okay, so it is more easy for oxygen to gain valence electrons and become fully filled than it is for him to lose it or it. And so it's going to have a -2 oxidation state. That's anything underneath it. Now we can get to fluorine, which has a -1 oxidation state, anything underneath it. They have 7 valence electrons, and because of that, it's easier for them to get to 8 valence electrons than it is for them to go all the way down to 4. Our noble gases, or anything vertically underneath helium, they have 8 valence electrons. They're super stable. They don't want to react with anything. You can say they have oxidation number 0, but just understand those are your only elements with 8 valence electrons, and it takes a ridiculous amount of pressure, temperature, etc. to get these elements to react with anything. Okay, so let's identify the oxidation number for each of these elements. Lithium, aluminum, tin, barium, and bromine. First, lithium, Li. Lithium is right underneath hydrogen, and because of that, anything underneath hydrogen is going to have a +1 oxidation number. That means it has 1 valence electron. Aluminum, Al. Aluminum is found underneath boron. Boron has a +3 oxidation number. So that means anything underneath it's going to have a +3, so that means aluminum has a +3 oxidation number. It also means that aluminum has 3 valence electrons. Tin, Sn. So tin is number 50 on your periodic table. That element is right under carbon, or actually, if you want to be specific, it's a couple squares underneath carbon. But we know carbon has 4 valence electrons. So that means tin also has 4 valence electrons, tin-4. Then we got barium. Barium is found underneath beryllium towards the bottom of the periodic table. It's number 56. And because barium is underneath beryllium, that's going to give it a +2 oxidation. Finally, we've got bromine. Okay, bromine is Br. That's going to be found right underneath your fluorine. It's number 35 on your periodic table. Okay, so if it's underneath fluorine, that means it's going to have a -1 oxidation number. Or in other words, it has 7 valence electrons. Because if we gain one negative, we're going to be at 8 valence electrons. The next thing is we need to identify how many electrons are given or gained for each of the following elements. So basically what I'm saying here is how many electrons or how many valence electrons do we have for each of these? Remember, a valence electron is either going to be given or gained. So this is where our pluses and minuses come in. If it is a plus, that means we're going to get taken away. We're wanting to give it away. Okay? It's easier for them to get rid of those electrons than to take on more. If it's a minus, then that means they're going to take more electrons on. So sodium, Na. Sodium is found on your first column of your periodic table, right under hydrogen. That means it has a +1 oxidation. Because it has a +1, that means it has 1 valence electrons, and that plus sign means it's willing to give up that valence electron. Now we have calcium, Ca. That's number 20 on your periodic table, and that's underneath beryllium, so it has a +2 oxidation. Same thing as sodium. We have a +2. That means it's going to be more likely to give those 2 electrons away. Then you have phosphorus, P. That's going to be found on the right side of the periodic table, somewhere around like underneath nitrogen. Nitrogen has a -3 oxidation number. Okay, that means it's more likely to gain 3 valence electrons to have a fully filled shell. So phosphorus has the same oxidation as nitrogen. That means it has the same valence electrons as nitrogens. That means it's going to take in or gain 3 valence electrons. Let's see, silicon, Si, that's number 14 on your periodic table. It's right underneath carbon. They have a +4 oxidation number, so that means it's going to give up or get rid of 4 valence electrons. And then finally, potassium, K, that's going to be found on your first column once again, so it has a +1 oxidation number. That means it's going to give up or get rid of its 1 valence electron. So that's how many it's going to get rid of. The key things you take away from this oxidation trend is if it's a positive number, so +1, +2, +3, +4, in other words, hydrogen through carbon, then you are going to get rid of them. They're more likely to get rid of those electrons. While if it's a negative number, -3, -2, -1, it's more likely to gain that many electrons. So those are going to be more on the right side of your table, nitrogen through fluorine. So what is the point of all this? What does this have to do with anything? Well, oxidation numbers determine how reactive an element is. They also determine how elements interact with each other. But the biggest thing is it allows us to predict the chemical and physical changes that can occur. So it allows us to say, hey, something that like lithium. Lithium wants to get rid of 1 valence electron. Okay, it has a tendency to do that. Well, fluorine has a tendency to gain a valence electron. So if you put those two in the same vicinity or same area, they're going to naturally react. It allows us to predict reactions a little bit more consistently and easier. I hope this video helped you. Oxidation numbers, it's just going to take a lot of practice. So don't be afraid to ask questions. Don't be afraid to seek me out. And saying all that, keep up the good work in the class, and good luck with your assignment.